We've now seen the concept of a quadratic form, and we've also associated the concept of a quadratic form to the concept of Hermitian matrices. Every quadratic form is naturally associated to a particular Hermitian matrix. And we know a lot about Hermitian matrices. For example, the spectral theorem applies to every Hermitian matrix. And remember what the spectral theorem says is that every Hermitian matrix S factors as Q times D times Q conjugate transpose, where Q is a unitary matrix, meaning that its conjugate transpose is its inverse, and D is a diagonal matrix with real entries on the diagonal. Essentially, and this follows from the fact that every Hermitian matrix is diagonalizable, and the eigenspaces of a Hermitian matrix are orthogonal to one another, and all of the eigenvalues of a Hermitian matrix are real numbers. Well, let's say that we have such a spectral factorization, and let's look at the quadratic form represented by this matrix S. The formula for the quadratic form is variable vector inner product with S. But if S is equal to Q times D times Q conjugate transpose, then we can substitute that in. We're now looking at the inner product of the variable vector X with Q times D times Q conjugate transpose multiplied by the vector X. And one of the things we said about matrices inside of an inner product is that we can move them to both sides or move them around in the inner product. However, every time we move an inner product from right to left or left to right, we have to conjugate transpose that matrix. So let's move this Q on the right over to the left-hand side of the inner product. So now we have our formula for the quadratic form as Q star multiplied by the variable vector X, inner product with D times Q star times X. This is kind of interesting because what we can do now is introduce what's called a change of variables. Let's define a vector y as Q star times X. This can now be substituted into our formula for our quadratic form. If y is Q star times X, and the quadratic form is the inner product of Q star X with D times Q star X, our formula for the quadratic form then becomes y inner product with D times y. And the example we saw in the last video said that, well, if we're looking at a variable vector inner product with a diagonal matrix times that variable vector, there's a nice formula for this inner product, which is the first diagonal entry of D multiplied by the first variable squared, plus the second diagonal entry of D multiplied by the second variable squared, and we keep going until we get to the last diagonal entry of our matrix D, multiplied by our last variable squared. So this technique is called completing the square. And the idea is that if we manage to find a spectral factorization of the matrix representing our quadratic form, the quadratic form itself might have a very ugly formula, but by completing the square, we can change our variables from x's to y's via the formula y equals q star times the variable vector x. And now the formula for the quadratic form looks pretty nice. It's the first eigenvalue of the matrix S times the variable y1 squared plus the second eigenvalue times y2 squared, and we keep going until we get to the last eigenvalue times the last y squared. And an observation we can make from this technique is that the definiteness of a quadratic form is determined by the signs of the eigenvalues of the Hermitian matrix corresponding to that quadratic form. And we can state this more rigorously as a theorem. Let's say that the quadratic form we're studying looks like the inner product of x with s times the vector x. So S here is the matrix corresponding to the quadratic form. And remember, this is constructed by building an n by n Hermitian matrix by looking at every term in the quadratic form and using those coefficients to build this matrix. Well, it turns out that the quadratic form is guaranteed to be positive definite if all of the eigenvalues of this matrix are positive. The quadratic form is guaranteed to be positive semi-definite if all of the eigenvalues are non-negative. The quadratic form is guaranteed to be negative definite if the eigenvalues are all negative numbers. The quadratic form is negative semi-definite if all of the eigenvalues are non-positive. And the quadratic form is indefinite if some of the eigenvalues are positive and some of the eigenvalues are negative. So if you manage to find all of the eigenvalues of the matrix representing the quadratic form, all you have to do to determine the definiteness of that quadratic form is look at the signs of the eigenvalues. So here, let's look at an example. Here we have a quadratic form on 3 variables, and the formula is negative x1 squared plus 2 times x1 times x2 minus x2 squared minus 2 times x3 squared. The matrix representing this quadratic form, well, let's look and see how to build the coefficients really quick. I like to always start with the diagonal, and here the square terms are negative x1 squared, negative x2 squared, and negative 2x3 squared. This means that the diagonal of our matrix is negative 1, negative 1, negative 2. And there's only one other non-zero term here, and that's 2 times x1 times x2. So we should chop negative 2 in half, or sorry, we should chop plus 2 in half here, and put half of it in the 1, 2 position, and the other half in the 2, 1 position. So here in the 2, 1 position, we get a 1, and here in the 1, 2 position, we get another 1. And all of the other terms need to be 0 because there are no other terms in our quadratic form. Let's look at the characteristic polynomial of this matrix. So remember, we're taking t times the identity matrix and subtracting this 3 by 3. So here's the determinant we're trying to take. And it's easiest to do an expansion about maybe either the last row or the last column, where we can immediately pull out t plus 2. So this reduces to t plus 2 multiplied by this 2 by 2 determinant. And when we expand out the 2 by 2 determinant, we manage to factor the characteristic polynomial, and we end up with t multiplied by the quantity t plus 2 squared. Well, once we have this factorization, we immediately know the eigenvalues of S. One of the eigenvalues is lambda equals 0, because setting t equal to 0 gives a root here. And another eigenvalue is given by lambda equals negative 2, because setting t equal to negative 2 gives another root here. So the eigenvalues of our matrix here are negative 2 and 0. This tells us that the quadratic form is negative semi-definite because both of these eigenvalues are not positive. They are non-negative numbers. But this is not a negative definite quadratic form because one of these eigenvalues is 0, which is not negative. So we now know that this quadratic form is negative semi-definite, but not negative definite. So what this means is that no matter what numbers we plug into this quadratic form, we will always spit out numbers that are not positive, but we might spit out numbers that are equal to 0. Let's look at another example where we have a spectral factorization. So here in our example, we have a spectral factorization of a 3 by 3 Hermitian matrix. So this is an expression where S is a 3 by 3 Hermitian matrix equal to Q, which is a matrix that's 3 by 3 with orthonormal columns, times D, which is a 3 by 3 diagonal matrix with real diagonal entries, and Q conjugate transpose. How can we read this data? Well, the data on the diagonal of D gives us the eigenvalues of S. So here, the eigenvalues of S are 6, 3, and 0. How do those eigenvalues interact with the columns of Q? Well, the first column of Q should be a unit vector that's an eigenvector for S, where the eigenvalue is 6. The second column of Q should be a unit vector. That's an eigenvector of S, where the eigenvalue is 3. And the third column of Q should be a unit vector. That's an eigenvector of S, where the eigenvalue is 0. Well, we can now apply the technique of completing the square to the quadratic form represented by this Hermitian matrix. Remember, to complete the square, we define a change of variables where a vector y is set equal to q conjugate transpose times the variable vector x. Once we have this substitution, we know that the formula for the quadratic form is first eigenvalue 6 times the new variable y1 squared plus the second eigenvalue 3 times the second new variable y2 squared plus the third eigenvalue 0 multiplied by the third new variable y3 squared. So this third term will drop out because we're multiplying by 0. But what are the other two terms in terms of the x's? Well, if we look at y1, y1 should be the first coordinate of q star multiplied by the variable vector x, which is really the first row of q star, 1 over root 2, negative 1 over root 2, 0, multiplied by the vector x1, x2, x3. And that product ends up giving us 1 over root 2 multiplied by the quantity x1 minus x2. So that's our expression for y1, which we should then square according to our formula. What about 3 times y2 squared? Well, y2 should be the second entry in q star times x, which should be the second row of q star dotted with the variable vector x1, x2, x3. That ends up giving us 1 over root 3 times the quantity x1 plus x2 plus x3 as y3. So now we have a more convenient expression for our quadratic form. The original quadratic form had input variables x1, x2, x3, but by introducing this change of variables, we managed to write our quadratic form in a more convenient manner. The quadratic form is 6 times y1 squared, where y1 is equal to 1 over root 2 times the quantity x1 minus x2, plus 3 times y2 squared, where y2 is equal to the quantity, or is equal to 1 over root 3 times the quantity x1 plus x2 plus x3. It's worth noting in this example that we can clean up the algebra a little bit. 1 over root 2 squared is 1/2. So if we pull that factor out, we get 6 over 2, which is equal to 3. And 1 over root 3 squared is equal to 1/3. And if we factor that out, we get 3 over 3, which is 1. So one thing to note here is that this quadratic form is positive semi-definite because the eigenvalues are 6, 3, and 0, which are all non-negative. But this is not a positive definite quadratic form because one of the eigenvalues is 0, which is not positive. Okay, so let's talk about another technique for determining the definiteness of a Hermitian matrix. So the problem here is that the technique we just introduced, which was called completing the square, involves a spectral factorization of the Hermitian matrix representing the quadratic form. But to calculate a spectral factorization, we need to find the eigenvalues of that matrix. And in general, finding the eigenvalues of a matrix is hard. So a question to ask, therefore, is how could we more efficiently determine the definiteness of a matrix? Well, it turns out that if we can factor our matrix S as L times U, where L is lower triangular and U is upper triangular, we can actually determine the definiteness of S by only looking at the pivots of U. So let's say that we have S equals L times U. It turns out that S is positive definite if all of the pivots in U are positive. S is positive semi-definite if the pivots in U are all non-negative. S is negative definite if all of the pivots are strictly negative. S is negative semi-definite if all of the pivots are non-positive, and S is indefinite if some of the pivots in U are positive and some are negative. Now, we should issue a word of warning here, because when we've done LU factorizations in the past, we've often needed a matrix P in that factorization. And the theorem we just stated will only work if S is factored as L times U, and it won't work if the matrix is factored as P times S equals L times U. So let's see an example where we can just apply the theorem. Here, we have a 3 by 3 real symmetric matrix, which is therefore a Hermitian matrix, and this matrix is factored as L times U. Well, the pivots in U are -3, 1, and -3. Well, some of these pivots are positive and some are negative, so this immediately tells us that S, as a Hermitian matrix, is an indefinite Hermitian matrix, because some pivots are positive and others are negative. Here's another example. Here we have another 3 by 3 real symmetric matrix, factored as L times U. The pivots in U this time are 9 and 1 and 1. Well, all of these pivots are positive, which tells us that S is a positive definite Hermitian matrix. So as soon as we factor it as L times U, we know the definiteness of our matrix.